Hey everybody, Johnny here. In this video, we're going to take a look at this new geometry node setup that I've created. This setup automatically generates PVC pipes using a simple mesh as your driver. By adding these extra boundary points, you have control over how long each of the joint pieces are. Not only does this node tree work with angled joints, it also works with multiple joints like T's. This one's going to take a bit of explaining, so let's jump right into it. For this tutorial, I'm going to be using the current release of Blender, which is 3.2.0. First of all, we'll clear out our scene, and I'm going to add in a simple mesh. I'm going to delete one of these points and extrude this line a little bit so we have something to work with. Let's jump over to the Geometry Nodes tab. In thinking about this problem, I figured there were three sections I needed to deal with. One was the pipe itself, second would be the angle joints, and third would be the T-joints. So let's tackle those a step at a time. We'll start with the easiest one, which is the pipes. Adding a new node tree, I want to start with a mesh, so that later on I can apply this modifier and have it changed into a static mesh. So to turn this mesh line into a tube, easiest thing would be to use a curve to mesh node. And since we're starting with a mesh, we'll have to change it into a curve first. So we'll use a mesh to curve node. Our mesh is now a curve, and so now we can use a curve to mesh node. And for the profile curve, we're just going to use a simple curve circle. So at the very beginning here, let's go ahead and tie our resolution and our radius of our pipe into our group input. Alright, there we go. Now because we're going to add curves to the corners of our pipes, we'll go ahead and add a fillet curve node. We'll put it in poly mode, add a few counts, and there we go. Let's go ahead and reduce the radius of our pipe a little bit. Next, we're going to want to give our pipe some thickness. Since there isn't a solidify node yet, we're going to use a few nodes to create our own. First, we'll use an extrude mesh node. We'll tie our curve geometry into that. We want to turn off individual faces, and we want to plug this into our output. We want our offset scale to go inwards, so we're going to need a value like -0.01. Now immediately, it looks like something went wrong, but not quite. What we've done here is extrude all of the faces inward, but it didn't leave the original faces. So we'll simply join the extruded mesh with the original mesh. Now because our offset was negative, our new faces are pointed in the wrong direction, so we're going to want to use a mesh flip faces node to reverse them. So this little node setup will actually act as our extrude. I'm going to grab these nodes and press Ctrl G to group them. Now in this new little group, I'm going to take the mesh input and bring it over to the join geometry and get rid of the second one. And then I'll take my offset scale and tie it to the input. Coming out of this node, I'm going to call this one extrude. So now later on when I need to do extrusions, I have this simple node that I can add in. To make our pipe look better, I'm going to add a mesh set shade smooth node and turn it off. Now we have a nice clear end. So that almost does it for our pipes. The only other thing we'll do is add a material set material node, drop it in here, and tie it to our input. And we'll call this pipe material. So now we have easy access to setting that later. I'm going to go ahead and take all of these nodes and join them together. I'll press F2 and name this pipe setup, and I'll just move it up a little bit out of the way. The next piece I'm going to worry about are the multi-joints, or the T-joints. This is probably the next easiest one. So let me go ahead and add one to our mesh. Now because of the way the curve to mesh node overlaps itself, we're going to use that to our advantage in generating our T-joints. The basic idea we're going with is that I want to take this point where the multiple joints come together. Then I want to use any surrounding points to that point. So these 4 points are going to be left alone. Everything else will be deleted. And then those 4 points will be used to create a new curve to mesh node, which has a radius a little bit larger than our original pipe. But how do we find that? That's the question. To do this, we're going to use a couple of nodes that you probably haven't used much before. The first one we're going to use is called Vertex Neighbors. It's under the Mesh menu. This node will give us the vertex count and the face count. The vertex count is basically how many edges are connected to any given vertex. So if we look at this mesh, we'll see that the endpoints should have a value of 1, these middle points would have a value of 2, and this T would have a value of 3. So really, for these T-joints, or any junction point for that matter, is going to have a value of 3 or more. So we're going to use that to our advantage. The next thing we want to do is identify the 3 edges that we want to keep. In this case, that's these 3. And there's one thing that these 3 edges share that's in common. They all share one point that has a vertex count of 3. No other points on this mesh have that. So how do we find that? Well, to do that, we're going to use a node called edge vertices. So when our node tree is looking through all of its edges, this node can tell us what the index of the first vertex is, or what the index of the second vertex is for that edge. Up until recently, this wasn't terribly useful, but a new node called field@index is going to make that a lot different for us. I'll add that under the utilities menu. Field@index lets us go ahead and extract certain values out of a given field. Let's see how we're going to use it. I'm going to change this to integer mode, and what we'll say is, when we're looking at an edge, let's go ahead and look at vertex 1. Now, instead of looking at the edge domain, we're going to look at the point domain. The point domain is where we can get the vertex count. So if I plug vertex count into here, this value for every edge is going to give me the vertex count of the first vertex in that edge. Now keep in mind that edges don't have a set order of vertices. They're going to be random throughout your mesh. But that's okay, because what we're going to do is duplicate this and do the same thing for vertex 2. So now, as we look at each edge in our mesh, we're going to know the vertex count at each of its vertexes. And we can use that then in our edge calculation. So now what we want to do is keep any edges where either one is 3 or greater. So let's get if either one is 3 or greater. We'll add a greater than or equal node, greater than or equal to 3. We'll duplicate that for the edge 2. Now we want the case where either of these is true. So we'll add a utility Boolean math node and set it to OR. If any edge has one of its vertices with a vertex count of 3 or greater, that edge will be marked as true. Otherwise, it will be marked as false. So these 3 edges that I have selected will be the ones marked as true. I'm going to add a group input node here. So now let's put this into action. Take our original mesh and delete everything but these 3 edges. So now we'll add a delete geometry node. Plug in our incoming geometry, plug in our selection, change the type to edge, and route it to our output. Now immediately, you see that we've gotten the opposite result that we were going for. That's because we selected these 3 edges and then deleted them. So we'll want to invert our selection. In the past, we would have just added a Boolean math not node here, but there's a new option in the Boolean math node, and we can change this to NOR. NOR is basically an OR node that has a NOT node placed after it. You can think of it as saying this NOR this is true. So this will give us the selection of edges where neither of the endpoints have a vertex count of 3. And now you can see we get our T. From this point, we can go ahead, change this to a curve, and then add our curve to mesh node, just like we did above. Because this is going to be one of our fittings, we'll go ahead and add 2 more inputs. One for our fitting radius, one for our fitting resolution, and we'll add a set material node and connect this one in for our fitting material. I'm going to take this set shade smooth node and do Alt-P to remove it from this frame. I'll bring it down here and connect it to the output. I'll then add a join geometry node in front of it and connect in our new fittings. Our fittings are looking pretty good, except we need to go ahead and extrude them inward. Because we already created an extrude node, we can go ahead and add it through the group menu. And it's just that simple. We'll go ahead and take these nodes and press Ctrl J to put them in a frame. These will be our T-joints. Now what's nice is, because we did greater than or equal to 3, we can add as many junctions as we want at this center point. And they don't necessarily have to be at 90-degree angles. I'm going to go ahead and add a couple of materials. Now finally, for our angled joints, we need to do one more grouping. This one's a bit more complex, because while there is an edge angle node, there's no node that gives us the angle of a straight line of edges that don't have any connecting faces. So we have to find a way to determine what the angle is where two loose edges come into contact with each other. If I look at our mesh, we can see that we have endpoints which aren't connected to anything, so therefore they don't really have an angle. We have points like this that are in the middle, and so they've got a straight angle, like 180 degrees going through them. And then we have ones like this, where we have some kind of degree angle, this one being 90. If what we can do is look at each point, and then, if it's not an endpoint, look at the two surrounding points, and then compare the direction between those points. So, if we were looking at this point, if we look at this vector from this point to this point, and compare it with this vector from this point to this point, we can determine if those two vectors are in line with each other. We can do this using the dot product node. And in this case, we can use the dot product node to find out that these are pointed 90 degrees from each other. So let's dig in on how we can start to compare 3 points next to each other. So what we want to do is look at each point and look at 3 positions. The position of the point we're looking at, and then the point to either side. Now, because meshes can branch and be connected in multiple ways, there's no guarantee that the points of a mesh are in a specific order. So we can't use just the index of our meshes to determine if 2 points are connected to each other with an edge. However, in a curve, we are guaranteed that along any given spline, 2 control point indices will be one right after another. The only place where we would have trouble is at the endpoints. We'll have to treat those specially, but that's okay. So we're going to change our mesh into a curve first before we start looking at its points. If I take my group input and do a mesh to curve, now my mesh has been changed into multiple curves. And within each one of those curves, each point is going to be sequential. Now for each point, we want to determine how straight or bendy each point is. So we're going to store that in a named attribute. So if I go to Attribute, Store Named Attribute, I'm going to call this Straight. And it's going to be a float, because the dot product we're going to be generating will be 0 when the 2 angles are at 90 degrees from each other, and it'll be 1 when they're in line with each other. So how do we calculate this? First, we're going to need to get the position. So we'll do our input position. This will be the position of the current point we're looking at. Next, we're going to need the positions of the 2 points on either side of it. So to change our index, we're going to need the input index node. And just like we did before, we're going to use the field at index node. Once for the node before, and once for the node after. For the node before, the index we want is the index subtracting 1. So the index prior to the one we're on. And for the next one, we'll do the same thing except we'll add 1. What field do we want? We want a vector because we're going to be looking up the position at each of those points. So this output is going to be the position of the previous point, this will be the position of the current point, and this will be the position of the next point. Now we want to find the vectors between these points. We can do that simply by subtracting the current position from each of these. So we'll use a vector math node, set it to subtract, and subtract the current position from the previous position, and then subtract the current position from the next position. These are now the 2 vectors from our current point say this point in the corner to the previous point here and the next point here. Now to compare those, we're going to use the dot product node. But to make our lives a little easier, we're first going to do something called normalizing. We're going to take these vectors and shorten them so that they're only 1 unit long. This means our dot product of two normalized vectors will only be a value between -1 and 1. So if I go to my vector math and set it to normalize, my dot product will now be a value between -1 if the 2 points are pointed exactly opposite of each other, 0 if they're at 90 degrees from each other, and 1 if they're pointing in the same direction. However, I don't care if they're pointing exactly the opposite or exactly the same. So what I'm going to do here is take the absolute value of our dot product. If they're exactly opposite, they'll be 1. If they're exactly the same, they'll be 1. And if they're at 90 degrees, it'll be 0. So this takes care of all of the points except our endpoints. And since we have an endpoint selection node, we can simply use that to select a static value for our endpoints. So to do that, I will add a utility switch node and set it to float. I'll add a curve endpoint selection node and select the first vertice in the start and the last vertice in the end. If it's true that we're looking at an endpoint, we just want to set the value to 1. We'll pretend our pipe is straight at the endpoints. Otherwise, we want this value that we've calculated. And now, I'll go ahead and plug my output into this value. In the same way that we deleted edges for the T-pieces, we're going to do the same thing for these corner pieces. Except instead of looking at the vertex count for the 2 ends of each edge, we're going to take a look at the straight value for each of the endpoints. So we're going to take an input of our named attribute and our edge vertices node. We'll add 2 more field at index nodes, the indexes being the indexes of our 2 points, and the value being our straight value. So now, if we come across an edge where both vertices of that edge have a value of straight, we're going to delete that. Now, because we don't want them to have to be perfectly straight, we're going to use a greater than node here, and we can put some value like 0.8. Next, we only want this to happen when both of the ends have a straight value greater than 8. So we'll do a Boolean math node, set to AND. And now once again, we're going to use a delete geometry node, deleting edges with this selection. If I plug this straight into my output, you'll see that our mesh is still intact. The reason for this is you can't delete points out of the middle of a curve and create a hole. It just makes the curve go from one point to the next, ignoring the point you deleted. So in order to actually delete and make gaps, we need to change this back into a mesh before we do our deleting. So we'll do a curve to mesh with no profile curve. Now doing that, we can see only our angled bits are left. Now just like the others, we can do our mesh to curve and curve to mesh. And we'll want to reuse our fitting settings from before. Now, just like we did, we're going to need to add the same fillet node we did for our pipes. And then we'll also add our extrude node. You'll notice here that we don't have a disconnect between these two sections. If I go into edit mode, you'll see that there's really only one point between them. So if I move that up and add another one in here, you'll see we get the result we were looking for. And so to finish this up, we'll join these together and make this our angled fittings. Of course, any of these other settings, like the count and radius of your fillet nodes, the offset scale of your extrude, or the tolerance in your greater than nodes here, any of those could also be brought back to your group input for more settings and more control over your nodes without actually having to go into your node to make those changes. And since we started with a mesh and are ending with a mesh, I can also apply this modifier and change this into just a normal mesh. While you may not need to generate a PVC pipe maker, I hope you learned a few tricks along the way in this tutorial. And while there's of course other ways I could have done many of these steps, these are the ways that came to mind when I was putting this together. As always, I hope this inspires you to make something awesome, and until next time, I'll catch you later.